Now see here, for rendering, we need special rendering. And why is it so? Why special rendering is needed? Let us understand that. See, the idea is that when we will be splatting a scene, it might involve 1 to 5 million Gaussians. Based on the resolution and the complexity, a scene might involve around 1 to 5 million Gaussians, which is like very huge. Now, the nav rendering method, it is very inefficient, because in nav rendering, what we will be doing is that we will be testing every Gaussian for every pixel, and it's like a bottleneck. So meaning is that in nav rendering, what I'll do is that for every pixel of the screen that I want, I will be I will be testing every Gaussian, like to render one pixel, I will be testing 1 million Gaussians. Then to render the second pixel, 1 million Gaussian. So it is like highly inefficient. It is far too slow and compute intensive. So nav rendering I cannot do. I cannot test every Gaussian for every pixel. So that's why I have to bring some parallel computing into picture, and some innovation in the strategy. And that is what is tile-based strategy is about. In tile-based strategy, what I'm doing is that I am breaking the scene into tiles. So instead of processing per pixel, we divide screen into tiles. Typical tile size is 16 into 16 pixels. So I will break it into tiles. So 16 cross 16. So 256 pixels at a time I'll have like this. Now the advantage I get with this method is that local memory, because these tiles I can process it in local memory. No special memory is needed, because GPU shared memory very easily. These tiles, because 256 only pixels, so these tiles I can process it using local memory. Parallelization. This is very important, because all these tiles I can render parallelly. Tiles are processed independently, and that makes it very fast and reduced work. Because of this tile methods, now every tile will only consider those 3D Gaussians which will fall on it. So we will skip irrelevant Gaussians. So that's a very big thing, because it's not like every Gaussian will occupy every tile. It will never happen, because every Gaussian will have a position, size, shape, and orientation. So it might occupy 2 or 3 tiles. Let us suppose I have like a very big Gaussian, something like that. So it is occupying like 4 tiles at a time, max, or 5 tiles also. But it cannot occupy all the tiles. So we are skipping irrelevant Gaussians while processing a particular tile. And that's a very big computational advantage we get in the tile-based strategy. Now here, one more very important point to discuss is the frustum culling. So before rasterization, before even dividing the screen into tiles, we will remove Gaussians outside camera view. That is frustum culling. Frustum culling is removing the Gaussians outside camera view. Gaussian is discarded if center is outside frustum. If the center of the 3D Gaussian is outside the camera view, those 3D Gaussians will be eliminated. That they will not be considered. And projected size is negligible. And this is very important, because this reduces workload dramatically. This reduces workload dramatically. So this is like a very important operation, because see, in the raw scene without frustum culling, Gaussians may be millions, but after frustum culling, it might get converted into thousands or even lakhs. So that's very, so the idea is very clear that okay, we have millions of Gaussians, we will do the frustum culling wherein we'll get thousands of Gaussians. Now we will we will divide the scene into tiles will splat, will throw these 3D Gaussians on the tiles and will project 3D to 2D projection and then sorting based on the depth and alpha compositing. So that is the tile-based rasterization. Now, if I talk about tile assignment, for each Gaussian, like here I have a Gaussian like this is the Gaussian. So for each Gaussian, we have to compute screen footprint, like what portion of screen that Gaussian, the 3D Gaussian is occupying. And I have to determine which tiles it overlaps. And whatever tiles that Gaussian is overlapping, we have to add Gaussian to tile list. So in this way, we are now very sure that okay, each tile will only process the relevant Gaussians. And this is very powerful technique because out of thousands of Gaussians, it might be that a single tile might involve hundreds of Gaussians. And to process hundreds of Gaussians is like not very like a compute intensive task. So here we saw like how we are able to make like how this tile based rasterization architecture is so efficient technique, and hence because of this efficiency which we achieved, we are able to process it in the real time, because this frustum culling is like a very innovative process technique. And here you can see like out of so many 3D Gaussian, only the 3D Gaussian which are the part, the camera point of view, field of view, only those will be considered. And see this, the 3D Gaussians falling outside the camera field of view, they will be eliminated. Like they will not be considered.